So here's a challenging problem just in figuring out what they're asking here. What they're saying is that n can represent any positive integer, and they're asking you how many solutions will this equation have? Well, it turns out for different values of n, there are different numbers of solutions. And our goal here is to try to find the mathematical relationship between the choice of n and the number of solutions that that would lead to. The best thing that crossed my mind, first of all, was that if n has to be a positive integer, I might learn a lot about this problem with n being the first positive integer, which is 1. The problem didn't tell me to let n be specifically 1, but I thought I'd learn a lot about the problem if I explored what would happen if n were 1. If n were 1, then my original equation becomes this equation. Now, I solved this and I got these 4 answers, and I'll tell you how I got them. I applied the square root property, then realizing that radical 1 is 1, I've isolated the tangent and gotten 2 solutions. The tangent can either be 1 or negative 1. So I thought about my unit circle, and I thought about the fact that there are 2 places, notice the red, 2 places where the tangent is positive 1, and notice the blue, there are 2 places where the tangent is negative 1. And those are the 4 places where the tangent is plus or minus 1, and hence those are the 4 solutions to the particular equation when n is 1. Of course, the problem doesn't specify that n has to be 1, it just says that it has to be a positive integer. The next thing I decided to do was see what would happen if n were 2. Now, I'm not going to show my work here, but when n is 2, I solved this equation, and much scratch work later, I ended up finding 8 answers. There are, of course, more than 8 answers, but the problem specifies that it wants the number of answers on the interval from 0 to 2 pi. So out of infinitely many answers, there were 8 of them between 0 and 2 pi. And I thought I saw a pattern. By the way, I didn't show where I got all that, but you could do that using prior techniques. Let me just keep to the larger picture here. The next thing I did was to explore what would happen when n was 3. In other words, how many solutions did this equation have on the interval from 0 to 2 pi? Well, out of all infinitely many solutions, I found 12 of them. And again, I didn't show my work here, and it's not really the point. I'm trying to draw a bigger picture here. You could do this if you had enough time, although I'm not sure you'd want to. But let me continue with my point. I then, just to see what would happen, I let n be 4. In other words, I wanted to know how many solutions this equation had on the interval from 0 to 2 pi, and I found that there were 16 solutions. And you can see patterns in these, and maybe you could have done this quickly, and maybe it would have taken you forever. Either way, I think we've explored enough to see a pattern here. Here's a summary of what we just found. That if n is 1, 2, 3, or 4, that there are either 4, 8, 12, or 16 total solutions on the interval from 0 to 2 pi. And once you see all this, it should be pretty clear that in general, there are 4 times the value of n solutions to this equation. And that's technically the answer to this problem for n. But let me say a little bit more about how we could have saved the trouble of actually solving for all those solutions just to gain the information in this table. Remember, when n is 1, and we were solving this equation, there were 4 answers on the interval from 0 to 2 pi that would work. So we got 4 possible x values in that equation, just reminding you of that. Now for n equals 2, we could solve this equation using what I call the integer values of k method. You maybe have seen me do that, where I find all infinitely many solutions and express them with a parameter k. But rather than that, see if you can follow this logic to avoid all that hassle. If x is allowed to be between 0 and 2 pi, then 2x is allowed to be between 0 and 4 pi. I essentially just doubled the constraint. And here I'm thinking of 2x as an arc. And 2x can terminate at any one of these places. But since the arc 2x is allowed to be as large as 4 pi, there would be 8 values of 2x that would terminate at that location between 0 and 4 pi. And I didn't type it here, but if there are 8 different values that 2x can be, then there are also 8 values specifically that x can be, because you could divide them all by 2 to get them. Let's see if you can follow the logic again when n is 3. When n is 3, we're solving this equation. Now, if x is allowed to be between 0 and 2 pi, then 3x is allowed to be between 0 and 6 pi. I've just tripled the original inequality. That dictates where my solutions have to be. If you think of 3x as an arc, 3x would have to terminate at one of these places. And how many such places are there between 0 and 6 pi? Well, there are 12 of them. So there are 12 different values of 3x. But if there are 12 different values of 3x, wouldn't that mean there are also 12 different values of x? And the same logic applies to n equals 4. And this, without actually finding the solutions, we could have come to the same conclusion that we did before, that whatever the value of n is, there are 4 times that many solutions to this problem. Tough problem. I hope this cleared it up a little bit for you. That concludes the problem.